Welcome to the next session on advanced algorithms. Last time we started looking at the closest string problem, which is this problem. I just repeat the definition. We have given a few strings of the same length over some alphabet and also a threshold number. And we try to find a consensus string, namely one that lies in between all those so that it has Hamming distance at most k from any of these input strings, which means, so this s should also be of the same length. I should add it to the definition actually, but otherwise Hamming distance is not defined, and Hamming distance just counts the number of indices where the characters don't match. I don't recall whether I mentioned that this problem is actually NP complete. Not a big surprise. But it's also one of these problems where a direct reduction of the usual problems is not so easy. I thought maybe I could include a little reduction, but I didn't find a simple and direct one. But there is one over a certain number of hops. So the problem is NP complete, which is it's bad news for use in practice. I told you last time that in practice, you're often even interested in a generalization where you're not looking for a consensus for the whole string, but only a substring, which can be at a different position in each of the input strings. And that problem is even hard to solve by an FPT algorithm, most likely. So it's some W1 hard problem. But for the closest string problem itself, we'll see that we can find an FPT algorithm. Already last time we talked about this dirty column lemma, which is a very simple observation that if you have too many columns in this arrangement of the input strings where there's differences, then you won't find a consensus simply because there's one of these for all consensus strings that has too many mismatches. That was a simple counting argument. Now this time we proceed to the actual algorithm to solve the problem. Let's first give you the algorithm, and then while we prove that it's correct and it has an FPT runtime, you will probably understand better how it works and what it does. So it's given a candidate for the consensus string in this recursive definition, and the topmost call is closest string FPT, where you just take arbitrarily one of the strings, say the first, and if you're very happy and lucky, then you're happy. So if the first string is already one that happens to be a consensus, then you're done immediately. And we will see that in any case, you can start with one of the input strings, and you add the parameter k, which was the distance that you allow. Now in recursive calls, you see that we make this parameter smaller, so d is the number of symbols you are still allowed to change. And this will get smaller and smaller. So if at some point you find you should have not changed that many symbols, then you're certainly in a dead end. But if you at some point find that the current solution, S, is actually a solution to the problem, because it has at most k mismatches to any of the strings, then you just return that. And then there's a condition where we can also for sure exclude this branch of the search tree. We will talk about in a second why this is true. So if you find the distance between your current candidate and any of the strings that's too large, then you know there's no hope to get close enough to that string. Maybe it's intuitive enough that if you're allowed to change d more values and there's still more than k left that don't match, then you won't reach that string. You won't come close to that string. Now the interesting part is You don't have a solution that's hopeless, but you also don't have a solution for the full problem yet. That means there's some of the strings Si where you have more than k mismatches, so it's not yet a solution, but also not too many. And in that case, you pick all the mismatch positions and take a subset of a certain size, and then essentially try to modify your candidate by just setting that position so that it matches to that one string from the input. So you move a bit closer to Si, and you do that for a whole subset of the positions where you could do that. And then you do recursively a call with this new consensus candidate and one less allowed changes. Whenever you find one that satisfies the problem, you simply return it. And if none of these works, that's going to be the hard part to show that then there actually is no solution with that distance. I will start simple with the correctness proof. I'll show the algorithm later again. But first, let's build some preliminaries. So this is the formal proof that this abortion condition here is correct. If you have two strings that are too far apart, more than 2k distance, then you won't find such a consensus. And well, this is relatively simple. If you draw this, say this should be the consensus that you're looking for. And here's Sj, and let's draw just Si below again. Then you know there's a lot of columns where these have mismatches. So let's make a specific example. K is 3 and we have 7 mismatches. Then of course in each column this S can be either the position, the character of this string at that position or of that string. So you will always have at least one of these up here, no matter how you distribute them. You will have one of the strings where you have more than k mismatches. That's simple enough. I guess this kind of graphic by example proof is sufficient in that case. A more formal argument would be that the Hamming distance is a metric. We're not using that in the rest of the proof, but I think it's maybe helpful to just get a bit more acquainted with what that means. So a metric is a measure of distance defined on a set that has 3 properties. You might have seen that before. So first of all, the distance between any 2 points should be a weakly positive number. So this is true because we just defined Hamming distance to count mismatches. That's always 0 or more. Also, for the same string, the distance must be 0. That's also by definition. And the last thing is the triangle inequality. That's the only thing that requires a second of thought. So the distance between 2 points in our set must always be upper bounded by going to a triangle. So if you're more graphically inclined, so this is in Euclidean distance, this means the distance between these two is at most the sum of the distances if you go on a detour via y. And here, I mean, if you draw a circle down here and a circle down here, you see that these two together are much more in the typical case. And if y lies on this line, then you have equality. And this general form is what we call the triangle inequality. It's fulfilled by the Euclidean metric or by the Euclidean distance, which is why it's a metric. And it's also fulfilled by Hamming distance, by essentially the picture that we've just drawn. So the number of mismatches between these two can never be more than the mismatches between those and those, because all columns where Si and Sj and S are the same. So if Si is the same as S and S is the same as Sj, then also Si and Sj must be the same. That's transitivity of equality. And then you just sum up. Shall I elaborate? I think it's trivial enough. So this is a metric, and that means the triangle inequality holds. And from that we can immediately conclude that if we have the distance between 2 points is so large, so if this is Si and this is Sj, and their Hamming distance is already greater 2k, and there's just no way to find a point S so that it's within k distance of both. You will have more than k differences to one of the strings. Well, or both. So this essentially proves that we can apply this rule. Now here's what I'm trying to show now. The algorithm, here in small again, has essentially a search tree of size k to the k, which is not really small, but it's fixed parameter tractable because it's only depending on the parameter. Okay. You might think about whether you can improve that algorithm or not. So the fact that the algorithm is based on is that our consensus S must differ or can differ at most k positions from any input string. Okay, that was just reformulating the result. So if any candidate solution has too many differences to any of the input strings, then this candidate can't work. So we can't make it, so we can't modify it in a certain number of steps to match that one. You remember our dirty columns lemma from last time? This basically means you can, so for one thing, it's trivial that we can delete all non-dirty columns, right? For that, we only have the same symbol in all strings, so we simply copy that to the consensus string. And also, we can't have more than mk dirty columns. So that means the whole instance is at most consists of at most mk dirty columns, which essentially limits our length of the inputs. So this is maybe, strictly speaking, before we start with that, we should make sure. So in the proof, we can say without loss of generality, the length of the strings is at most m times k, and all columns are dirty. And in the algorithm, we would first delete all non-dirty columns, and if then there's too many left, then we reject right away. Okay, I excluded these trivial steps in the algorithm, but actually they should be there. Now let's look at the size of the search tree. That's the simple case. Okay, it's maybe a bit small, but still readable, maybe at least from the front row. We start with this distance k, and in any recursive call, we make it one smaller, and we stop when it's 0. So the recursion depth is certainly just k or smaller. That's a trivial observation. And the second thing, the fan out, so the arity of the tree, if you like, is just given by k plus 1 here. Maybe I'll write less or equal because it might happen that one of these is finishing early and then we don't even start the next one. But in general, you use, in the worst case, you have to check all of the k plus 1 different positions in this p prime set where you potentially can modify the consensus candidate. Okay? So this together means that the search space is just at most k plus 1 to the k. And this is O of k to the k. If you don't believe that, then you should calculate the quotient. I didn't believe it, so. But this is just this famous term that goes to e for k to infinity. So this is always smaller than e, and O requires the quotient to be bounded, to stay bounded.
Are you sure you didn't omit some kind of k on the right side of the equals?
I hope I didn't omit a k, so you first pull these together, so it's k plus 1 over k.
Well, what's that on the bottom? An alpha?
Oh no, that's also a k. I just divided by this one.
Oh, okay. Never mind.
Okay.
Sorry.
Yeah, I think it checks out. So this is for the size of the search tree. That was easy enough. Well, the theorem doesn't even talk about correctness. And this also doesn't, so maybe I'll just skip it. No. Just kidding. So the interesting part is the correctness. Let me add that. So now we should prove that. Okay. It's clear whenever we find a string that we return, this is a correct solution because we only return a string initially from this part and we don't change it afterwards. And there we explicitly check that it's a solution. So this is easy. If we return something, then it's also a consensus. We explicitly checked for that. So we have to show that if we abort, that there is no consensus. With a given distance. Now, let's assume we are in the interesting case. So we start with S1, and this is not directly a consensus. But we have a yes instance, so there is some consensus. Let's call this, what did I call it here? Okay, S hat. Now we should prove that we can find a branch in the tree so that we modify S1 into S hat. well, maybe for a suitably chosen consensus. The consensus is in most of the cases not uniquely defined, and yeah, it's maybe asking for too much whether we can find a specific one. We just find one if one exists. So by the how did I call this lemma here? No, it was here. The two different lemmas. So 2, 3, 42. Someone was picky about the numbers, so I'll add them here. So this means that for all I, the distance of our current candidate, and as I is at most 2k, otherwise we didn't have a solution. Now we consider all the positions for some of these as I. So that we have more mismatches than we allow. Let's consider this set P of all mismatch positions. So that's all J, so that S1 at position J is not SI. Yeah, SI at position J. So I'm writing these strings as arrays to not get into the position to use upper indices or something else. I guess the notation is clear enough if I comment on it. Okay, so rephrasing this one is just the set of mismatch positions is not too large. Now the algorithm picks a P prime with k plus 1 from this set and checks all of these positions if it's doable to set the consensus to that symbol of SI at that position, right? Now we call one of these positions that we check so we call a position J correct if J is in the set of positions P1, which is all the J, okay, maybe all the P, so that the first string at that position is different from this, so it's in the set P. And we're moving closer to our actual consensus. So these are steps that bring us closer to a consensus, and they are just helpful in that sense. But in principle, P could also be among the other set, which is just all P. So let's say P in P, so that these are different. Since our algorithm just, well, without any clever way, chooses one of these strings where we have at least more than k mismatches, we might also pick one that actually brings us further away from the consensus, from a consensus that we pick here. Well, certainly our set of all positions is just divided into these two. And because the distance of the consensus to this ith string must be at most k, actually this set can't be larger than k. Otherwise we would have more mismatches, even restricted to that set P. So and that means at least one j in the set P prime that we pick is correct. Okay, we pick k plus 1 positions from P, and there's in total at most 2k, and at most k of these are bad, so there's always there must always be one that we pick from P1. So P prime cap P1 is never empty. And now we essentially iterate this argument. So in each step, there's one branch that brings us closer to the consensus. And we always must have one of these strings as I so that there is a path. And that means if we just try all of these possibilities, we will find that path. So under the assumption that there is a consensus, and S1 is not directly a consensus, we will find one. And we'll find this one. Okay. Now we've talked about the size of the search space. The running time is a second step that requires you to look a bit closer, but it's actually not so hard. The first part here of the running time is just needed to read the input once at the beginning, which means that's the time that we can spend on deleting all non-dirty columns. So that's the pre-processing for deleting boring columns and checking whether more than m times k columns remain. I wrote this in quotation marks because I've said that the kernelization that we've talked about a few sessions ago is the theory of preprocessing in a sense. So it's a formalized, it's a formalization of what is a good preprocessing. Now in a sense, these steps are reducing the problem to a kernel, but it's not a kernelization in the definition of the theory because its size is not bounded by a function of the parameter. And in fact, I tried to find a kernel for the closest string problem, an interesting one, I mean. So we know there is one, this algorithm is an FPT algorithm, so we know there is this, bogus kernelization that just says either the instance is already small enough or I return a trivial one because I, in the process of preprocessing, already solved the whole problem. Oops. That was the proof that kernelization is the same as FPT. But this is not a constructive preprocessing step for the problem. I didn't find a nice kernel for this problem, even though it has a somehow nice FPT algorithm. It seems hard to find a natural kernel, natural kernelization. Okay, but still it's a pre-processing that we do up front, and afterwards L is at most m times k. So this was the size of the search space, which is essentially, so that's the number of recursive calls. So this should be a proportional to sign, not an alpha, because we counted actually the leaves, and the internal nodes might be a few more. Yes?
I was wondering, is there maybe some kind of theory on if the average string will usually be very close to the solution, because it kind of gives the feeling that the average string should always have like the minimum distance to all of its strings.
So the question was whether there's a theory for average strings.
Well, I mean,
the point is, what would you understand as the average string?
well, I mean, we already have the column view, so we could probably just count the occurrence of each.
So there's something called majority vote. You can just, from each column, pick the symbol that occurred most often and invent some type-breaking rules. So that might give you a certain heuristic, but I don't think that it will solve the problem in general.
Well, it's likely not to.
Yeah, okay, it's definitely not solving the problem in any easy sense. The problem is, of course, that you require, you have a strict bound for every input string, the number of mismatches must be less than k. And such a majority vote consensus would be good for a collective, so a social welfare kind of measure, if you just sum up the number of mismatches to all the strings or something like that. That's a simpler problem. I guess that won't be, so yeah, I think that's not hard. But here the problem is that you require it for every string, and that needs some trade-off between distances to this individual strings. You're absolutely invited to think about that. If I didn't find it easily, then it's maybe an open problem. So if you find a cool kernel for closest string, I guess that would even be interesting in practice. So for the analysis of the existing algorithm, what remains is to check that in the time m times k, we can do all the non-recursive actions in the algorithm. This line requires us to check the distance between the consensus and each input. Well, essentially we need the same information here again. And we can certainly do that in a linear scan over each of the inputs. I'm just wondering whether there's an m squared actually, because we have m strings, each of length m times k. Since it's an O, we can certainly add that, even if I'm mistaken at this moment. So let's go to the big algorithm. So for this step, I have, for every input string, I have to compute the Hamming distance. I can certainly abort the computation when I have found more than k mismatches, but in the good case, I have to check the whole string, right? And the length of the string could be m times k. So at this moment, I don't see why it's m times k. Maybe there's a simple argument that I'm overlooking at this point. And in any case, including the square doesn't make the bound so much worse, because the big part is I guess, in the k to the k term. And it doesn't make the statement wrong, at least. Yeah, and that completes the analysis of the running time of this algorithm. It's a good question whether you can improve upon that. And I think it's pretty sure that this is close to optimal, the algorithm. Maybe if we have time, I'll talk about lower bounds based on the exponential time hypothesis next time. And with some arguments like that, you can show that there's no algorithm that improves on this k to the k by much. So even though this algorithm is relatively simple, it's based on a simple idea. The only slightly clever step maybe was to limit this p prime only to k plus 1 positions and not take all of p. That's maybe the only non-trivial part. And that essentially gives you an algorithm that's probably not possible to beat. For today, I want to talk about something different. That's another strategy for algorithms, another technique for improving algorithms. I'm pretty sure this is wrong. LaTeX messed up the numbering. We had one chapter on theory, we had one chapter on kernelization and depth-bounded search trees, so this should be 3.4. Never mind. So the technique is called interleaving. And the idea is that up to now we've considered algorithms that reduce a problem to a kernel. Well, in the last instance, it wasn't even a kernelization in the formal sense, but it did some preprocessing, and then it solved the kernel by exhaustive search. And the same, so we followed the very same approach for the vertex cover algorithm, or at least it's a natural thing to do it like this. But in a sense, we can hope for that during this depth-bounded search, where we make the parameter smaller, we can hope for further improvements if we reapply the kernelization. That's at least something worth trying. In principle, this is always doable, but the question is whether it will be helpful. And to make it more specific, I'll make a few assumptions, and then under these assumptions we can study rigorously how much help it is. Essentially, the assumption is this. So we assume a kernelization. That's what we need for preprocessing. Normally, a kernelization would just give us that the size of the output is some q of k for some computable function q. And now we require that this is actually a polynomial. So I should add that probably closest string is out here. It's probably unlikely that we find a polynomial kernel for that problem. But for the problems that we had before, vertex cover, we had even a linear size kernel, if you remember the LP-based solution. For maxsat, we had a quadratic size kernel, and we had a simpler kernel for vertex cover that was also k-squared. So for many problems, you do have a polynomial-sized kernel. And k should run in polynomial time. That's just by definition. That's first half of the algorithm. The second is we have some depth-bounded search algorithm. And we assume for simplicity there's just one such branching step. You recall that I mentioned in general you could have many. You could have different rules, and they could have a different branching parameter, but we actually didn't see an example for that. So we have an algorithm that branches, where these are the reductions of the parameter. Well, and to check if this rule is applicable, and to check and to compute the reduced instances takes some time. And we assume that this is bounded by R of n, which is again some polynomial. So this second step is also a restriction in a sense, but not a very tough one. In principle, it could also depend somehow on the parameter, but for all the instances that we had, these were actually even low-degree polynomials, often linear time. And we assume that we have already solved for this specific branching vector the problem of computing the size of the search space, and it's just some alpha to the k for a constant alpha. So this is not really a restriction. Now if we go back to forget about interleaving, just run the algorithm, first apply k, then apply this depth-bounded search. Then we need p of n time to apply the kernelization. And then on the output of this thing, we run that one. Now we know alpha to the k is the size of the search space, which is, in terms of big O, is also the number of recursive calls. So yeah, let's just say number of recursive calls. And then each of these recursive calls has to do a bit of work for the branching, and that's given by the R. But now n, the input size, is the output of the kernelization, so that's why this is the time per recursive call. So usually we will assume that this is the dominating part of the cost, so this polynomial in the beginning doesn't really matter too much. But we have here, applied to this already large thing, we have to multiply this cost per recursive call. Now let's look at the interleaving idea. This is an excerpt of the branching depth-bounded search algorithm, which usually would just look like this. So if you ignore the first lines, then we have some instance and some parameter, and then we split it up into several cases. We know that some of these cases has to find the witness if there is one, the usual kind of thinking that we've seen in the examples. And these are somehow smaller instances with smaller parameters. But now before we apply our rule for splitting the instance, we check whether the instance is actually large. So C is a tuning parameter that we can choose. For the running time, it will not really matter which one it is, so that's something we can just leave open. And Q, remember Q was the size of the kernel. So the output, one more time, no? Here. That's the size of the kernel that we get by applying K. So if our instance is much larger than the kernel, we just apply the kernelization, which gives us some new instance and some new parameter. We just take this one and then apply the branching. Now what's the running time of this modified approach? We certainly have the same kind of recurrence as before. This is just the recursive calls with a modified parameter. But now instead of, okay, before we actually ignored that part. So initially we looked at this recurrence and solved it, and the solution for this recurrence without the additional part here was alpha to the k. Okay? So that was TL prime. Let's just write that down so that I can undo this here. That's what we essentially assume. And that's why in the running time bound, we had to multiply this alpha to the L by the cost for each recursive call. In this recurrence, we only counted the number of leaves. If we want to count the running time in the recursion directly, we should have this additional term, because each splitting costs us this toll term r of the size of the instance, roughly. The point is that we didn't do that before because this is actually a hard to solve recurrence since it involves L and K. So in general, the solution that we would like to have in the end should depend on K. So we should only solve this recurrence up to L equals K, and that gets kind of messy. So that's why we didn't do that. We chickened out by leaving out the inhomogeneous part, solving this, and then afterwards say, okay, hey, each recursive call just adds such a term, so it's just multiply that. Now for the interleaved part, we can't do that, because now here the size of the instance depends on the actual parameter in the search tree. That was just what we were aiming for. Now this here is essentially the worst case scenario in a sense, so we have to apply the kernelization, which had running time p. Q is what we had before. And this then is the splitting cost for the smaller instance. So we should now know how to solve these recurrences. In our case, with the assumptions, we know that this is actually some polynomial. And that's why we made these assumptions. And well, before I start with the math part, let's first finish off the algorithmic one. Here's another theorem on linear recurrences. Now we're looking at inhomogeneous ones, which means we add such a function in each recursive step. The rest is the same. And again, we look at this characteristic polynomial. That's the same as before. And we assume that this is the dominant root, which here means the root of largest absolute value of this polynomial. And we assume that this toll function, this term that we add here, is not too large. And this is actually, okay, there's a zero missing. This is actually easily fulfilled in our case. So in our case, f was actually a polynomial. So it's n to the c. Here I only require that it's a bit smaller in exponential growth than our c0. Okay? So this is definitely fulfilled for all polynomials, but we can make the theorem a bit more general. And then the result is that the solution of this recurrence differs only by a constant factor from the one that we get when we omit this again. Okay? So if we apply that theorem here, then this is O of alpha to the L by theorem 345. Because omitting these, that was just our t prime. And we have already solved that by assumption. And that's alpha to the L. Now if you compare that, this means that this factor is actually gone. Okay? So here we had the preprocessing plus alpha to the k times this polynomial. Now, I should have called the upper one t prime maybe. Here so this is r of q of k times alpha to the k. And now we got rid of this polynomial factor in front of the alpha. And this is essentially what the interleaving gave us, which is pretty cool. Now, we should talk a bit about how to prove this. I'll try not to dive too much into this, but a bit. So we've seen last time that we can use generating functions. To solve the recurrences when this is missing, and we can use the same thing with a bit more machinery if this is present. So we had split up the initial conditions, t d minus 1 c to the d minus 1. And then we found that okay, let's again write this. We sum over all these parts. So that was inserting the recurrence here. Oops. dj. Okay, now I have no sum over n. I skip one step because you've already seen that. Now we have the mismatch that we start here and here. We have to pull out z's. Now this is some polynomial in z. Let's just give it the name. And the new part, f. The new part that we had when inserting the recurrence here was that we also have this fn. So we have here something that's essentially the generating function of this function f. So we define this to be that. And we'll see that we know a bit about this generating function by our assumption. So by the same shifting indices and pulling out these tricks as we had before, we get this to match the definition of t of z with only a few things in front. And we have to subtract, because here we start at di, but we should start at start a bit before at dj. We have to subtract a few of the initial conditions again, but this is also just a polynomial of degree at most d minus 1. So and then we could solve this equation for the generating function t. that was given by this. Let's give these names again. So this is the numerator. So let's say n of z. Maybe the denominator should also get a name. Let's call it denominator of z. Okay. Now for these kinds of functions, so I should say something about n of z, n of z. The p and q are just polynomials, which are very, very harmless functions, because polynomials are always entire functions, which means they're defined for any value you put in. There's nothing that can go wrong. And they're also always smooth in the sense that you can take derivatives as many times as you like. And they're all continuous and so on and so forth. About our f, we can, yeah, okay, it might be that this is a bit too weak. We maybe need also some form of regularity. But we know that so it's a polynomial plus f. We know that this function, it's given by a power series. And we know that these terms don't grow too large. That means f is analytic for all z with smaller absolute value than the c0. Now for most of you, analytic is a cryptic term. It's part of complex analysis, and I won't go into any details. But formally, we just need that this function allows inserting c0 without causing any problems. And it should also be, so analytic means you can take derivatives in the complex plane, which is a bit a stricter assumption than real derivatives, because they can come from any of the directions in the complex plane and they all have to agree. Since it's given by a power series, you know that you essentially can take derivatives, because if the power series is absolutely convergent, you can take derivatives term-wise. And taking term-wise derivatives inside of here is easy enough. And we will just assume that this is given, and we use it as a black box in the theorem later. So let's take a small excursion to something that's called singularity analysis. I will skip many mathematical details in the sense that I just tell you how to use it, because it's easy to apply to many cases, extending those ones that we need here. It's I think nice enough to have seen it once. To keep it simple, we stick to a function that's given by a numerator and a denominator. We assume that this is just a polynomial, which it is in our case. And we assume c0 is the root of this polynomial, now with smallest absolute value. So you might remember that in the theorem we use this polynomial where we take this one, replace z by 1 over c, and then multiply by c to the d, which means that all roots of this polynomial are the roots of this one if you take the reciprocals. So 1 over the roots of these are the roots of these. Okay. That's why we now look at the roots of smallest absolute value. And we assume that this numerator can be any function as long as it's analytic, this cryptic term that you may translate as smooth enough. I think I need that this is a real root. In general, a polynomial has also complex roots. But you can prove if the coefficients of this generating function f are positive, then there's always a real root of this kind. Okay, this is the setting that we assume here. Then you've already seen in some detail before that we can rewrite this 1 over d of c as partial fractions. So last time I've written down the full general form. So in principle, we sum over the zeros, over all zeros of d. Then each of these zeros has a certain multiplicity mu. And then we have terms that have some constant that depends on these two. And a single term in the denominator that looks like this. 1 minus c over the root to the j, where j has this range. That was exactly what we had before. Now it's just written in the concise notation with the sums. And we've already seen last time that from all these terms, there's essentially only one that dominates the coefficients of f. So what we now do is we approximate this function for values that are near this this root. If we have a root of d of z, that means this function has a problem at these roots, because then we divide by 0, right? Such points are called poles in that case, and they are a form of singularities. Singularity in general is a point where you can't take complex derivatives. And one reason why you can't take complex derivatives is that the function is not even defined at this point. Because at the pole it should be plus or minus infinity. Division by 0 is just not well defined. It converges to positive or negative infinity at this point, but it might disagree depending on the direction, whether it's plus or minus even. So the function is not well defined at this point, and you can't take derivatives, and that's why it's a singularity. So all the roots of dz the singularity of f of z. It's a point where the complex derivative doesn't exist. I just note it here for completeness, even though we haven't talked about what complex derivatives are. The idea is that we approximate the function near such a singularity, and one can prove that this doesn't affect the coefficients by much, so that we can extract from that such an approximation, an asymptotic approximation of the coefficients of the function. Okay, phew. That's the idea of singularity analysis. Now, again, a little sidebar here. You might have heard of Taylor expansions of functions. If we have a function that is infinitely often derivable, so you can take derivatives infinitely often, then this is actually an equal. You can write this function as a power series where you take higher order derivatives at a certain point. So, okay, this is another function than before, and this z0 is not necessarily the one before. This is in this sidebar, it's just a general formula. So it's a Taylor expansion of f around z0. So this is an exact representation of the function, assuming that this exists. So that means that you can take derivatives infinitely often. So for example, this is true for all polynomials. There you can always do that. But you can also truncate such an expansion, and then you get an approximation of a function. So the first term, if you set I to 0, is don't take a derivative, but take the function itself, divide by 1, and then multiply by nothing. And the second term would be first derivative, divide by 1, and this. And then you might decide that this is the precision that you're interested in. So you truncate here, and you simply put the next term. Okay, now I'm out of paper here. Okay, let's do it in the next line. Ooh, I have to copy the complete. So I'm using the plus minus here because O terms for me are always in terms of the absolute value of a function, which means that this it's giving you an error bound. We're giving a term up to a certain precision. So this would be the next term in this series would be one with a square here and some constant before it. Constants can be ignored in the O, but now we have an O term that doesn't use n to infinity as a limit, but it's for the limit that z approaches z0. Remember that we are looking at approximations of a function around a certain point, namely around this point z0. So that means we're considering a limiting process where the argument of the function converges to this point. And that also means that we get more precise if we have smaller powers here, because this difference here will be something small. So it's all just the other way around as for the ordinary big O's where n goes to infinity. So this, for example, means that terms like this are in big O of 1 minus c over z0 to the b whenever b is larger. Because if you divide this by that, then you get this to the a minus b. If a is smaller than b, it should be larger. Sorry. If a is larger than b, then we need more paper. So this is the continued box. To prove this, we just take the quotient. This is 1 minus c over c0 to the a minus b. Now this is larger than 0. So that means this is, if you insert here z0, you get 1. Take minus, then it's 0. And 0 to something positive is fine. That's just 0. So this is 0 when z is going to z0. So here the limit actually just exists, and it's 0, which means the quotient stays bounded. It's even going to 0. If you like, I can write here a small o. This is also true. Whenever we take this quotient, then this is in small o of this. So that means any larger terms of the Taylor expansion where the power here is larger than our 2 are swallowed by this o term. Okay, so now we know how we can approximate functions. One last thing, this is actually just rewritten. It's the same to say z minus z0 or 1 over this, because you can just divide by z0, and then because I'm talking about big O, I always take the absolute value. So if you take this to some power a, that's the same. You just have to pull out the c0 that way. And then you can also write it the other way around. And this is only a constant, so in terms of O, it's the same in terms of theta. Okay? So, to wrap up, we can approximate a function by using its Taylor series, truncate it to a certain precision that we would like to retain. And we can even write the error term in this form that we used for the functions before. So let's actually do that. Now, okay, I didn't talk about when this works. Taylor series always exists in this form when the function is analytic. But this is nothing but the definition. Here we need to be able to take derivatives as often as we like, and analytic is just complex derivatives. And one interesting feature of complex analysis is that if a function can be derivated once, you can take derivatives of any order. It's the same. Since our function n is analytic, we can apply it to this function. So we approximate n of z by its Taylor series. And I even truncated one term before. So we only take the constant term, this one, and then the next one is already the O term, plus minus O of this. And as I said, we can rewrite it as 1 minus c over c0 to the 1. Okay? A good thing about Taylor series expansions is that you can apply them a function remains analytic. If you multiply two analytic functions, then the product is also analytic. And that's why we can approximate one factor and the other factor individually. Okay. Now the other factor is this partial fraction decomposition. And there we do essentially the same thing. We also approximate it, but we don't even care for computing such a Taylor expansion. Simply by looking at the terms, we know the one that is dominant. So we take the value for 0 for the root of smallest absolute value. And we take the one with the highest j, because these are negative powers. So the largest j gives you the least power. And here in this regime where we go to the set 0, we should have the smallest power is the dominant term. That's the term that we retain. And we can show that all others for C0 are actually in this. So here it's minus mu, because this is in the denominator, plus 1. Now this partial fraction decomposition also consists of many other terms, namely all those from the other roots. But for the other roots, I can simply insert for z the C0, and what I get is just some number. So all others are just given by some constant. In terms of an approximation near C0, all the other terms are given by a constant. Because the functions are well defined there, I can simply insert the value C0 as C. Okay, this is an approximation for the function as c goes to C0. Now simple things we can just multiply out. And this also works with the O terms. And what remains is this term. And you can check that actually this is the largest error term that remains. So you should compute all pairs, but you multiply this by a constant. That means this is at least the error that we have, and all others are just smaller. So you multiply this by that. That makes the power here just one larger, and so it's actually the same. And this O of 1 is much smaller than this as error term. This is something you can just compute and use this rule here. So this is still an approximation. Now at some point in time you might be asking why I'm doing all this. And the reason for that is this. Okay, it should all be under this heading. The reason why I'm doing all this is this theorem, which is the core of singularity analysis. Okay, we're having a function, and I included this because otherwise it's not rigorous. I won't discuss it. This is just fulfilled. Delta analytic means that the function so here's point 1, and that means that the function f is analytic in such a circle. So this is point 1, and you can make the argument a bit larger. This is the complex plane. Maybe just forget about it. Our functions fulfill this property, and in case you want to apply this to some other function, you will have to learn what this is. Now we have the function as an approximation. So this is our C0 in the general case. It's you can always make a substitution of the variables. So in general, it's sufficient to look only at one, but we can use it for the C0 also. You have a function that's approximated by another function and by an O term. So this is the approximation. This is the error of the approximation. And the theorem says that this is a notation for taking the coefficient. So if this is a generating function, then this is the coefficient. So this is Fn if this is given by this power series. Okay, it's just a notation to extract these again. The coefficients of f are given by the coefficients of g, which hopefully are easier to determine, and a certain error term, but now in the very usual and easy n to infinity world. So this is an ordinary O term like you know it. So what this theorem gives you is that you can approximate a function, a generating function in the world of generating functions with this strange kind of approximation that I've just sketched, Taylor series and so on. And you can translate this approximation back to the world of sequences of numbers. And this big O transfers to this big O. Okay? For our function, our f was approximated as n of c0 times this constant c that came from the partial fraction decomposition. So these two are just some constant, right? So also this is a function where you inserted something, it's really a constant because we inserted a constant. And then we had the 1 minus c over c0. And this whole thing is our g. Then we had the O term. Now if we substitute c for c times c0, then we have exactly the shape of this. And that means we can apply this theorem to take coefficients of this and this separately. And we just get an error term for the coefficients. Okay, we still have to take coefficients of this, but the constant only moves out. That. And we simply copy this. The only difference is when we make the substitution, then we get a z0 to some power. Okay, this is, maybe I should, I'm a bit running out of time, I know, but if you insert this, and you get just this, so you can say this is the coefficient if you insert that. And if you insert this product here, then you see that these are just canceling to z, and then you have the form of the transfer theorem. So all that happens is now we get a z0 to the minus n in front. To the mu minus 1. And the last step is to compute this coefficient. And this is actually something you can look up. It's simply given by a binomial coefficient. And, well, very briefly said, because this is so nice, so okay, and you also have this c0 that I forgot. So if the simpler form would be that, if you simply have this without the c0, what's the coefficients of that? Okay, let's first leave it like that. Even if this is a negative power, like here, we can use a generalized form of the binomial theorem. So the binomial theorem, you know, is like this. To the m. M minus n. This is n. And you can generalize this to actually any real number m, which is pretty cool. And in that case, the sum gets infinite. But you still have binomial coefficients here, but generalized ones, where you also allow any real number up here. And then you get one term, and the other is this 1. And you can write it like this. So the generalized, so this would just be minus mu to the n falling over n factorial. So that means minus mu times minus u minus 1 times minus u minus 2, and so on, and n terms of that. That's how you can define binomial coefficients for any upper index, even if it's any number. Okay? Now, last step, then I'll finish for today. If you take the coefficients of this, on this side it's easy because this is essentially c to the n. So the coefficient of c to the n here is this minus mu choose n. This is just 1. And then we have minus 1 to the n. And then there's a famous equality for binomial coefficients, which is called negation of the upper index. And that magically fits here. So this identity is true for any number k. That's a natural number because binomial coefficients are not defined for others. But any r, even if r is any negative number or so. And if you check here, then this is exactly the right-hand side for certain choice of r. Namely, oh, there's one missing. So we can apply it backward to this. Apply this here, then you get n minus mu minus 1 plus 1. Choose n minus 1 to the n. And here these cancel. And these cancel, and then it's minus mu choose n minus 1 to the n. And then we're there where we claimed. And this binomial coefficient can be, so this is this up front and then a power of n. And we should divide by this factorial, but I'll stop here. So we should briefly finish where we started here. So for our actual function up here, we have this form that we had that I discussed at length now. So we can insert z0 here for the n. We take the dominant part of this d down there. So after this long digression, the Tn can be written as some constant, which is essentially this, times the constant from the partial fraction composition that we could compute if we would like. and we have to divide by this mu minus 1 factorial. That's for the multiplicity of the root of z0. And then the actual growth part is c0 to the minus n and n to the mu minus 1. And we even get an error term that says it's this up to an n to the minus 1. And then finally you see that this is all just some constant, and this is the solution of the homogeneous part where you drop the f. So this proves the theorem, even if you might have get lost in the details here.
Vor etwa einer halben Stunde.
Yeah, that's. I know it's a bit of a digression, but maybe when you see it another time, you find it as nice as I do. We can solve these recurrences in a very general setting, and the machinery here is quite helpful. So algorithmically, what we've seen is that the interleaving of kernelization and depth-bounded search seems to be of help. What we'll briefly discuss next time is that we've only analyzed upper bounds, or we bounded the worst case in a sense, and it might be that only the analysis is just too coarse to see the difference. Maybe we just should improve our analysis for the non-interleaved part. Next time I'll show you briefly an example that this, at least for a specific example, is not the case, and that interleaving really helps to improve the algorithm. Stay tuned.